And yes, so we actually have to finalize today the part related to the operational amplifiers. I guess it was this one. Yeah, so we discussed in. Okay, yes, we discussed actually multipliers. So, and now we still have something to talk about, speaking about the circuitry. So we consider now another type of functional amplifiers. It's actually provide some operation like integration or differentiation. And one of the examples is the integrating amplifier that is demonstrated here. This amplifier, so actually we have a capacitor included in a feedback, and if we try to write down the balance for this, some equation for this amplifier, so first of all we certainly could define input current as a ratio between input voltage and the input resistor R. The signs we have here in a feedback. Also, it's a capacitive, but still we have a feedback. So we actually have a zero. We have a virtual zero here, and then so we know what currents flow in, and this current should flow through the capacitor. But now remembering from the theory of capacitors that the charge, what is accumulated inside the capacitor, from one hand, it's integration from the current. So we take an integral over the current, adding all current together through some certain period of time. So this will be actually an accumulated charge. And from the definition of the capacity, the voltage is proportional to this accumulated charge. So this is a relationship between the voltage over the capacitor and the current that flows through the capacitor. In fact, if you're going to calculate the output voltage, we just have to know that the circuit will be inverting. So we have a minus here. The currents flow, the positive current flow in, so the voltage here should be negative, because here we have a plus is accumulating, and here we have a minus is accumulating. So the voltage should be negative, because actually capacitor is connected to the output in reversal manner. So here is a zero and here is a minus. And then combining the current with the expression for the voltage over the capacitor, we get that the output of the integrator will be proportional to the real integration of the input voltage. So the problem of the integrator is, so even with sometimes even with a zero voltage on the input, we still have some bias current flowing partially through the capacitor. So the capacitor has so the capacitor will be charged by the bias current, which is not it is not a characteristic of the ideal amplifier. It's already a characteristic of the real one, of the real amplifier. So, but it has this bias current, and the integrators are tending to drift. Besides, if we have some alternating voltage on the input, so that's usually is not a problem, because the input voltage actually discharge the capacitor. But for when we apply some constant voltage, we have to from time to time to discharge the capacitor, or take some measure to prevent this, to correct this accumulation of charge by adding some negative, by putting some, but adding from time to time some negative input voltage. There is an example how it could be, how the integrator could be operating using two switches, which one switch is this first switch preload the capacitor to some initial output voltage, and the second just connect the input current. So this is one of the way how the integrator are used. But in fact, indeed, the output voltage will be just integration from the input voltage. Some of the use of integrator, it's a charge amplifier, where an example is shown here. These charge amplifier are used for the piezoelectric devices. As you know, the piezoelectric devices being deformed produce some current for a short time, but the problem is that if you deform the piezoelectric device and it actually got some voltage on the output of the device, this voltage drops with time, actually diminish with time because of the leakage current via the body of this piezoelectric device. So they have the leakage current, so it couldn't keep a constant voltage. So that we have actually are forced to integrate the current what is produced during the deformation to get the output which is proportional to the integral over the velocity of deformation, which is actually will be proportional to the velocity. In this way, we actually may actually fight with this diminishing of the output voltage of the piezoelectric signal. And this is quite an effective method to cope with the piezoelectric devices. So the output actually will be proportional to the deformation of the device. To prevent this saturation that comes due to charging of the capacitor because of bias current, the additional quite high resistance may be added in parallel. It little bit shifts the operation of the circuit from the pure integration, because we got here some output that will be proportional to the input voltage, not the integral of the input voltage, but nevertheless it helps to prevent saturation, and still the output will be related to the deformation of the piezoelectric device. One interesting example is not actually because we are just actually start to speaking about such a circuit with a capacitor in a feedback. Going a little bit aside, here is one interesting example of the circuitry that is used for the microelectrodes and has a capacitor feedback, capacitive feedback, but please note that this circuit has a positive feedback, so the output of the amplifier is connected to the non-inverting input of the amplifier. This circuit is used for the microelectrodes that have an extremely high capacity. So, and in fact, the capacity of the microelectrode is so high that if we are going to measure the voltage produced, for instance, by the single cell via this microelectrode. So the microelectrode is one that's inserted into the single cell. So the capacity, shunting capacity of this, the shunt capacity of this electrode is so high that any change in the internal voltage, internal potential of the cell will be actually shortcutted by this capacity, and our amplifier, which is connected to the microelectrode, may just see nothing. But here we use some special circuit that could compensate for this high capacity. And the idea is that, so first of all, we use here the positive feedback. The second, the amplifier, what is shown here, is not an operational amplifier, it's just some differential amplifier with a finite gain. The instrumental amplifier may work well here. So the theory of the circuit is like this. So let me consider that we have this part, the capacitor CF, in a feedback circuit connected to the amplifier. So the equivalent circuit of this amplifier with a feedback capacity look like this. So we have actually in parallel the input voltage is connected here. So we consider that the input impedance is infinite here. So then actually the input voltage causes a current flowing through the capacitor CF, feedback capacitor, and the equivalent output voltage source that actually represents the amplifier. So the input current have to flow like this. So it has no input into the amplifier because of high input resistance. So if we consider the circuit, we may write immediately that the voltage, input voltage, is applied to this chain, the capacitor and the equivalent voltage generator that produce the voltage A times U in, where A is the gain of this amplifier. So this voltage is divided by two voltages. So we have actually the series connection. So the voltage over the capacitor plus the voltage over the amplifier, the voltage source. And let's add these voltages together. So we get such an equation. And we may calculate from this equation, we may calculate the input voltage, relate this input voltage to the voltage over the capacitor. So make sure what we have done here. So I subtract A times U input into from this side, actually to move it to that side, to the left side, and then I divide it all by 1 minus A, to get just a relationship between input voltage and the input current. So if I look at this expression, please note how it looks like. If we come back to how the voltage over the capacitor is related to the integral over the current flowing through the capacitor. So we have this kind of equation when C is a capacitance of this element. So if I look at this formula, this equation now, the shape, the pattern of the equation is the same. So I have the input voltage, I have this integral over the current flowing through the system. And here I have some coefficient. So in some extent, I may say that this circuit behaves like a capacitor, with a capacitance 1 minus AC feedback. So if A is greater than 1, it means that this value will be negative. And if this circuit behaves as a capacitor, so from the point of view of the source, my signal source, I have the parasitic capacity of the microelectrode CS, CC, coupled in parallel with some effective capacitance of this circuit, of this amplifier. And adding those capacities together, I will get the total capacity which is connected to my source, so this CC and this parallel capacity of all this amp, they all adding all those together, I get that the total capacity will be this CC plus 1 minus A CF, that CF is the feedback capacity. So it means that I may find the value of amplification coefficient, high enough to get this sum equal to 0. So if I presume that my capacity CF equal to CS, so CF equal to CS. So if CS. So if those capacities are equal, so actually A should be equal to 2. And that means that this scheme, this circuit, works like a negative capacitor. So what actually it's doing, so if it feels that there is some current trying to flow through CS, charging CS, this circuit immediately add additional current to fill up this CS to load it as fast as possible. So if otherwise the current is flowing out of CS, discharging it, this capacity, this circuit provide an extreme current by this way to discharge the capacitor CS as soon as possible. So actually it works like it's actually compensating this capacity. So it's quite interesting circuit with a effectively negative capacitance. So actually what does it mean, negative capacity? We push the charge inside, but the voltage drop of the element goes down. Or we rise voltage over the element and the charge starts to flow out of the element. So this is the idea of the negative capacity. Quite interesting circuit and really used for the microelectrodes. And another example of the amplifier which use capacitance is a differential amplifier. But when we integrate, we had a capacitor in a feedback. Here we have a capacitor on the input circuit. So when we actually have to write down that the input current is proportional to the derivation of the voltage over the capacitor, what in this case we have a feedback is just an input voltage, because here we have a 0 because of feedback. Yes, so it means that the voltage over the capacitor will be just input voltage, and the current through the capacitor will be proportional to the derivation of this input voltage. Well, so the output voltage is just a current flowing through multiplied by the resistance of the feedback. So this is an output voltage. Generally, indeed, the output will be proportional to the derivation, the first derivative of the input. The problem with the differentiating amplifiers, they are actually are tending to oscillate. So, and generally, the derivation procedure, as we know, it's increased noises always, both in the digital processing and the analog processing. So, if we have some oscillation of the noise on the input, this oscillation of the noise on the input will be amplified by the differentiating amplifier. So, actually, we may use this differentiating amplifier, but we have to know that it's actually prone to oscillation. Sometimes adding a parallel capacitor to the resistor actually little bit one more it's introduced some inaccuracy. The output will not be a pure derivation now, but it helps to prevent an oscillation and reduce the noises a little bit. Okay, so this is actually the review of all the functional amplifier. Another portion, another topic what we have to discuss, it's so-called frequency-dependent circuits. So we consider here the differential and instrumental integrating amplifier without specifying what type of the signal do we have. So we're just looking on all the physics behind the operation of this oscillator and get this relationship between the input voltage and output voltage as the integration of the input or differentiation of the input. For the frequency-dependent circuit, we actually, in fact, these two circuits what we discussed, both integrating and differentiating, they will be the frequency-dependent circuit because they contain elements whose impedances are frequency-dependent. But for the frequency-dependent circuit, it's actually, we may consider both these examples as a frequency-dependent circuit, but we very seldom indeed consider them as a frequency-dependent because it is not our goal to make these frequencies frequency-dependent, but it's just their feature. When we speak about frequency-dependent circuit as our goals, as our object of interest, the first device what should actually come in mind is filters. So we're actually trying to we use a frequency-dependent circuit to handle different frequency signal differently. And for this, we actually, when we're going to calculate a frequency-dependent circuit, we just took a certain particular circuitry, and use the approach we often use to calculate the AC circuitry. So we replace all the voltages by those complex images. We replace all the elements, passive elements like inductors, capacitors, and resistors by the complex impedances, and then we just calculate. We could get afterward. We could get the amplitude frequencies. We consider that the input signals are sinusoidal with a particular frequency omega, cyclic frequency, and then we just calculate the amplitude frequency response and the phase frequency response of the device by looking on the ratio between complex output voltage and complex input voltage and taking the absolute value of this ratio giving us an amplitude frequency response, and taking the argument of this complex ratio, it provides us a phase frequency response. I just don't going probably to consider, we took it as a separate, I think, practical calculation session. So for instance, I may took one of the typical examples of this frequency dependent circuits is so-called is an active first order low pass filter. So this is a low pass filter which we have here. We have here the input resistance, the feedback resistor, and the feedback capacitor. So I have to replace this capacitor with some kind of impedance actually. So we know that I replace a capacitor with the impedance 1 divided by G omega C, where G is imaginary 1. So if I do so, I use the same method as I calculate this. Actually, I just combine both RF and CF into a single impedance. One moment. We take a So let's take a look on how we calculate this. So I'll replace this CF. I take a red one. I'll replace the CF with the impedance ZC, which is equal to 1 divided by G omega CF. And then I will draw over. So again, I get actually here some parallel connection of two impedances. They are if the feedback resistor impedance and ZC. So if I calculate for these parallel connections, the total impedance 1 divided of Z by all of feedback at all together, this parallel connection will be 1 divided by RF, which is an reciprocal impedance of this resistance, plus G omega CF, which is reciprocal impedance of ZC. And then from this immediately I get that ZF will be equal, actually for the parallel connection, RF times 1 divided by J omega CF divided by 1 divided by J omega CF plus RF. So this is actually the parallel connection. So here is this impedance of this parallel connection divided by input impedance, which is just a resistor. If I make all the make all the algebraic transformation of this number, of this relation, of these ratios, I will get finally quite a straightforward solution. So that the relationship between output complex amplitude and an input complex amplitude will be just a ratio between frequencies, between resistors. What this is actually the gain for the DC case, yeah, if I consider the DC case, times a term which is related to the frequency. The tau, the number tau, it's a time constant which is actually equal to multiplication of RF by CF. So this is a time constant which actually describes how the device, at what frequency device start to suppress higher frequencies. So we have seen already this term when we calculate the first order filters, just passive filters, and if we take the absolute value of U in out to U in by absolute value of gain, we will get minus RR Ri 1 divided by 1 plus omega squared tau squared, as we had already. It's very similar to the low pass filter low pass filter form equation for the passive filter, but it's multiplied by the ratio Rf to Ri, which is actually the gain. So we have really, we name those filters as the active because they has an amplification for those frequencies which go pass through filter, and so it's actually providing an amplification too. So here is an example of the high pass filter when we actually added the capacity on the input, and then we if we make a calculation, so I have to take the feedback impedance, what is actually just ZF, which is equal to RF, just resistance of this feedback resistor, but the input impedance is a sum of the impedance of the capacitor and Ri, so I actually have this sum. Make a transformation, make algebraic transformation. Here I will got this equation. So it looks very similarly as its previous equation. So I have a DC gain, or gains or frequency independent gain. It should be a DC gain if I remove my capacitor, replace my capacitor with just a wire. Yeah, and then some frequency dependent term. So I get some frequency dependent term, and this frequency dependent term, so for this our gain as a function of frequency will look like minus Rf divided by Re. And here will be omega tau divided by, I'm sorry for this, here is a square root. So here is the square root 1 plus omega square tau square. So this gain depend on the frequency. So the first one, gain depend on the frequency in this manner. The higher is T, the lower is gain, something like this. And here I have dependence on gain, something like this. So I have a low frequency, a high pass filter. It pass by higher frequency. So then T goes to 0, with omega goes to 0, the ratio goes to 0 too. Here is an example of band pass filter. So the band pass filter here have a two feedback, two times constant T input, which is C input R input, and T output, which is C feedback R feedback, and dependent on and we have to be careful when designing such kind of filter, because we have to have the filter characteristic something like that. So we have a characteristic from the high pass, from the low pass filter, which is this one, and which has some certain frequency omega output, which is equal to 1 divided by T output, and we have to have some, this characteristic will be multiplied by the high pass filter characteristic, which looks something like that, with a frequency omega input, which is equal to 1 divided by tau input. So certainly for the filter to be able to pass something through, we have to have omega input less than omega output. For this, the tau input should be bigger than tau output. Otherwise, we may get such a situation when the high pass filter starts to cut from some very high frequency, but low pass filter already starts to cut from frequencies that has not reached yet the high pass filter pass band. So as a result, so this is the high pass, the low pass filter suppress higher frequency, the high pass filter suppress lower frequency. The multiplication on both these parameters give us that the filter doesn't allow to pass any frequency, so it will just cut all the frequencies. So this should be, you should be careful when you're designing the band pass filter. The expression, the characteristics, the amplitude frequency response of the high pass and low pass filters, it's very convenient to use a border plot to depict the characteristic of the filters. So, and for such kind of filters, for the body plot, when we plot the logarithm of the frequency and the logarithm of the amplifier, of the gain, sometimes the logarithm of the gain sometimes could be expression in decibels. It may be expression in decibels, yeah, but may be expressed just drawn in logarithmic, in a logarithmic scale. If it's expressed in decibels, so then we actually usually have the axis of decibels. So here we could have a gain in decibels, and here we have a frequency in a log scale. For the body plot, when the one decade length, or the length, I speak about real length. It means about real length, the scale. So this length and this length are equal. In my picture, they are not equal. I speak about the distance between two ticks depicting one decade in a logarithmic plot. So for this, the graph of the first order field, for the first order filters, the diagram for the frequency response of the first order filter looks somehow like that. So we have some pass band, a pass band, and we have some stop band, and the slope of the stop band of this part of the curve, when the gain starts to depend on frequency, it will go exactly over the 45 degree, so as a bisect of the 90 degree. So here I have a wrong scale, so I have to compress a little bit the x-axis, the frequency axis, to have this distance equal to this distance. In this case, I will get this line going over the 45 degree. In fact, of course, so the curve, it looks quite similar to this. For the real filter, of course, they are not so far, how to say, this deflection point is not so well defined. So in fact, the curve looks like that. So it will be softened. This slope change will be softened a little bit, but nevertheless, we're very close. So if we add one filter after another like that, so we have one first order filter, then we get a second first order filter. As a result, we get a second order filter. And for the second order filter, the slope of the fall down part will be higher. So it will be, for the first order filter, the sloping part comes over the 45, at the 45 degree angle, this will be a half of the 45 degree. And then for the third filter, if we add 1, 2, 3 first order filters together, we get a third order filter. For this filter, the slope will be even more higher. So we actually divide in two the angle between vertical line and the previous order filter. So the higher is order, the more filters we get in line, the the sharper will be our amplitude frequency response. But very seldom in practice we use more than third order filter, especially in analog form, just because this adding of all these filters dramatically increases phase shift between the input and output. So to control a little bit the phase shift, there's an order of filters that really may be used seldom exceed 4. Usually it's a second, third order filters. So one more. So just repeat. So the body plot, it's a plot of the amplitude frequency response in a double logarithmic scale. So here is an example of low frequency filter. Here is an example of high pass, the low pass filter, the high pass filter, and here is a band pass filter drawn in a body plot. So they are, how to say, this for the first order filter, so we have such typical curve. Okay, so this is shortly about the frequency dependent circuits. Some nonlinear circuits, what is worth to discuss. So here is one of these, of such a circuit when we don't use an amplifier with a feedback. So we use here an amplifier, an amplifier without a feedback as it is, providing some reference voltage on the one of the inputs and providing the just voltage we are dealing with, input voltage to the other input. So how this circuit behaves? So actually when the output voltage, if you connect like this, the reference voltage is on plus, on non-inverting input, and the input voltage is on inverting input. So the operational amplifier without a feedback works like that. So when the input voltage is less than referent, so the plus input is at higher voltage than minus input, the output will be just a positive saturation voltage. So we just have here a positive saturation voltage. If the input voltage become greater than reference voltage, so we actually have the minus has a higher potential, the plus, the amplifier comes to the opposite saturation mode. So it just saturates, but with a negative voltage on the input. So because we remember that output is a proportional, so the output is A times U plus minus A minus. So if at plus we have a higher voltage than at minus, we get positive voltage. If at plus we have lower voltage than at minus, we have a negative voltage. So actually this will be the behavior of such a circuit. The question is why we need this circuit. Actually, the comparator, it's a first transformation from the analog, or like some kind of like a bridge between analog circuitry and digital circuitry or impulse circuitry. So it's actually required us to convert the analog signal in some type of the bistable signal with only two possible outputs. In this example, if we use just a usual amplifier, we can use a usual amplifier as a comparator. So the outputs of the comparator may be on either minus saturation voltage or plus saturation voltage. So in fact, we may code this minus state as 0 and positive state as 1 or vice versa. So we actually get some binary coded signal. In fact, it is not very good solution to use an operational amplifier as a comparator, especially if the amplifier is compensated and has internal capacitors to enhance to increase the bandpass of such an amplifier. But there is a specific circuit which is named the comparators, and they are often are working in the unipolar environment. So they have the output 0 if the input voltage is lower than some reference, and they have output of 1 if the voltage input voltage is higher than reference voltage. So they are working in unipolar environment. But still, if you have no comparators at hand at the moment, you may replace it just with a single op amp in a saturation mode. The speed of operation, so how fast this operation is for the amplifier, is not so bright, not so big, because when the amplifier is in saturation, it has some time to go out of the saturation when the input voltage changes. So it's not so very fast. So for the very fast switching, for very fast data transition, so we need we need to use a dedicated comparator. So specific circuits, specific integrated circuits that are named as comparator. But for the low process, the op amp is fine. With any comparator, whatever comparator do we have, whether it's just an op amp used as a comparator or it's a dedicated comparator, just a single level comparator has it's prone to some kind of errors, and this errors is related to the noise in the signal. For example, if you consider the quite pretty noisy signal, which change dramatically, so we may get such a situation when the signal goes over the level and the comparator switched to 1, for instance, over the level, but then because of noise, the signal drops down beyond the level, and this will be the indication for the comparator to switch back to 0, and it switches back. Then it goes up one more. So if a noise is high enough, so the comparator may feel a number of such switching on off, and as a result, our signal will not be made like, 0, 0, 0, then it exceeds some certain value, then 1, 1, 1, then it drop below some certain level, it's actually 0, 0, 0. But every time it's passed through the level, it's provided pulses. So the front end of the output signal from comparator and the end, the rear end of this comparator, that will be actually compromised with a number of these erroneous pulses. Could you imagine if this signal will be, for instance, a pressure wave signal? Use it to calculate the heartbeat rate. So it means that for every pressure beat, a very hard contraction, we will got more pulses that require. And if those pulses could calculate it or count it with a digital counting system, so as actually get an extremely high heart rate, it's actually not the case. To prevent this redundant or erroneous switching, the comparator are supplied with a so-called hysteresis. So the hysteresis socket, then this hysteresis socket for the operational amplifier, the hysteresis socket appears as a positive feedback, For this particular switch, we still have nothing interesting because, actually, because the system switched from high output to low output when the voltage on the inverting amplifier will be just changed from negative to positive. So it will be negative when U is lower than Uref. And we take the Uref, actually, we have to take this Uref negative. Yeah? In this case, so when Uref is negative and output voltage is lower than Uref, the sum voltage here will be negative. If your input become higher than Uref, which is negative, the total sum here become positive, and the comparator switches. So the switching will look like this. But if we add a divider here in a positive feedback circuit, so what we actually get? So when we have plus here output, which correspond to the negative voltages, this plus comes here through the divider, and the voltage here increases a little bit over the zero. It will be higher than zero. So it means we have to increase the input voltages a little higher than your reference, much higher than your reference, to get here the positive voltage to switch the comparator. And the same, when we switch the comparator and the voltage here drops to negative, the negative voltage appear here. It means that we should to reduce UE well below that Uref by value to switch the comparator back. So the resulting circuits looks like this. So when the signals actually when we comes from the positive voltages, and here the positive voltage, our input should go well below that Uref, and then this difference become low, to have this difference here to be lower than the voltage applied here. The voltages come here due to feedback. So the switching to the opposite side happens at lower voltages than Uref. And then we come back to the situation when U input is lower than Uref by some delta, and the comparator is a positive state. So when we goes up, when we increase, so if we have here a plus, we have here plus. So, and when we go back, so we need to get here the positive voltage, which will exceed this positive voltage going through the feedback circuit here. So we have to increase the input voltage a little bit higher than Uref by some delta for the comparator to switch on. So the behavior of the comparator looks like this. So it switches on or switches to negative by this way. But when we reduce the input voltage, it's switched by that way. So we have so-called hysteresis. So the way, it's a way one direction, it's a way in the opposite direction. So we have see here a hysteresis loop. Such a comparator with a hysteresis has a special name. It's named the Schmidt trigger. So what is actually the advantages of the Schmidt trigger? So let's consider we have some noisy signal and some level when the noisy signal have to switch on. So when the signal exceeds the noise, this level, the comparator switch on. So the comparator changes state. But when it changes state, because of the feedback, the level is changed too. So and if we're looking this example, this is example with the usual comparator. So it's when the level is exceeded, it's changed to plus. But this positive voltage on the output is like, so part of this voltage is subtracted from the level. So the level drops down. And then if even we have some oscillation due to noise, this oscillation due to noise doesn't fall down will not fall down the level. And we have no any switches. But if the signal goes down noticeably, so not because of noise, but it goes down noticeably, so it will be some moment when the signal drops below the level and the comparator switched back, and the level for the comparator level and signal level for comparison, the reference level will goes up. So and then one more, some change on some jumps in the noise of the signal due to noise will not actually exceed a new level now. So such kind of adaptive level for the switching. We have here some such kind of adaptive level for the switching, and this is actually helps much. Such kind of Schmidt trigger operation, it helps much. It's allowed to prevent the poor contact on with push buttons and so on. It prevents the effect of noise when you're going to set some level detector. So the Schmidt trigger actually it's a typical solution, typical example for the different kind of level detector. And we have to switch on a certain level of signal. So the Schmidt trigger prevent from multiple switching because of noise. So this is actually shortly the review what I'm going to discuss for the amplifiers. We still we'll discuss some additional circuits depending on context. When we'll speak about the sensors. So some sensors require some certain type of amplifiers to work with or circuits to work with, and we discuss it when we discuss an appropriate and a corresponding sensor. Now some comments about the real amplifier. So what actually is the difference between the ideal amplifier and the real one? And first of all, probably the one of the most important, that we in fact has no infinite frequency response. So the frequency band of the real amplifier is not wide, infinitely wide. So actually it's clear because the real amplifier it's some kind of transistor circuits where we have a p-n junction capacities in the transistors. We may some special introduced capacities. We have some lead wires inductances. So and that means that this feature actually prevent an amplifier from working at a very high frequency. So at the very high frequencies, just the transistor doesn't work. So the p-n junctions just allow to pass a high frequency current through the junction independent of the direction because of the capacity. So first of all, the real amplifier has no frequency, no infinite frequency response. Another example of the non-ideality is so-called offset voltage. So we discussed all the way that the output is equal to 0 when the input voltages are ideally equal. For the real amplifier, the output will be 0, when the output is 0, not necessarily the input voltage is exactly the same, so they may a little bit differ. It's because of the different input resistance on the two amplifier inputs. So we have some certain transistors on the input, and they will be a little bit different. The bias currents, so the currents that flow into the input or out of the input, they are not actually 0. They are still very small. For cheaper amplifiers, they are of the order of nanoamperes. For the more accurate, for the more precise amplifier, for the more expensive amplifiers, they are order of 10 amperes. They are very small indeed, but they are not zeros. They actually are real. And the output input impedance is not infinite too. So the input impedance is infinite, also very high, of the order of mega ohms or even giga ohms, and the output impedance is not zero, it's quite low, about 40 ohms usually for the typical amplifier. So what actually we get from these non-idealities? First of all, speaking about frequency response. If you look how the gain of the op amp depend on frequency, so we could see such kind of curve like this. So at lower frequencies, the gain is very high, but when the frequency increase, the gain actually drops down. First of all, so this gain of the amplifier itself, without any feedback, is named as the open loop gain. So it doesn't provide a feedback, the negative feedback for the amplifier, and it's actually we name it as an open loop gain. So open loop gain is very high at high frequencies, but drops down low frequencies, but drops down when the frequencies increase. What important also is very important that for the amplifier circuit, it's a three-stage circuit. So we have three stages there. We have a input. We have a first stage. It's a differential amplifier. The second stage, it's some kind intermediate amplifier, and we have output stage, the D-type output amplifier. So the D-type, I mean that it's combined from two complement transistors, to provide both positive and negative output. Well, if we have a three-stage, every stage actually behave in some extent as a first-order filter, as a RC filter, because there is a parasitic capacitance inside. So every stage at the very big frequencies, at the very high frequencies, introduce a phase shift up to 90 degrees. So we know that RC chain or RC circuit could provide the shift up to 90 degrees at the very high frequency. So here we have three such stages. Every one may provide up to 90 degrees. So it means that maximal phase shift may be even to more than 270 degrees. So actually, it means that if we provide a feedback for such an amplifier, it may happen that even we provide a negative feedback, so we connect the output with the inverting input. So the increase of the output have to cause increase on the output, has to cause increase on the input, which in turn which in turn causes the decrease on the output. This relationship may be shifted by 180 degrees. So we actually rise up the output voltage, the output voltage, which rises up output voltage due to over the feedback, cause increase of the input voltage, and increase in the input voltage has to cause decrease on output. But because of the 180 degree of half a period shift, so the input voltage increases, but the output voltage increases too, because there is a shift of the half a period, for instance, for periodic signal. So we got through the inverting input, we got not a negative feedback, but a positive feedback, and the amplifier circuit with the feedback starts to oscillate. To prevent this oscillation, we have to drop this phase shift below 180. And for this, a special capacitor is used. This procedure we change the frequency response artificially by adding a compensating capacitor actually in parallel to all three stages. Because of this, what we actually lost a gain. The gain of this amplifier will be lower the gain of non-compensating amplifier. We lose a response time. We lose in response time. The response time become higher because we actually have to now charge and uncharge this capacitor. So, for example, for the comparators, which doesn't operate as with a feedback, the use of the compensation is not necessary. So for the comparator, non-compensated circuits are used. The compensation itself may be done externally In this case, like old-fashioned amplifiers had a special two outputs when you have to put a capacitor in between. And more often used amplifiers, they already are internally compensated. The compensating capacitor is already in the chip. So that's why the amplifiers doesn't oscillate, because they have a compensator. They are compensated. Okay, so this is the first. The next one, well, so, and if we add a compensating capacitor, the open loop gain on the amplifier look now like this. So we actually see that with a higher frequency we get a lower open loop gain. And if we try to use this amplifier to make some real circuit like inverting or non-inverting amplifier and provide a feedback and get a calculated gain of this amplifier, actually we may provide this gain only in the frequency range when the open loop gain exceed the calculated gain of the circuit. So for instance, if we design an inverting amplifier with an amplification of 10 by taking feedback resistor 10 times higher than input resistor, the gain 10 will be, we will have a gain of 10 up to the frequencies when the open loop gain is higher than 10. At the higher frequencies, when the open loop gain drops below 10, we never could get the amplification of 10 for our inverting amplifier. So the circuit, the designed circuit, couldn't have a gain that is lower than the open loop gain of the corresponding op-amp. If we select the gains, the smallest gain, A equal to 1, so then we get the highest bandwidth for the amplifier. So for the open loop gain will actually we may look at which frequency the open loop gain of our amplifier will be equal to 1. So this frequency is called as the single gain bandwidth, and it's one of the important parameters of the amplifier. In fact, it's a multiplication. It's actually the product of the circuit gain and the circuit bandwidth. So we may immediately understand what will be the bandwidth, I mean the maximal frequency our circuit will work, knowing the circuit amplification, circuit gain, and this unit gain bandwidth of the amplifier. So it will be constant. So the higher I have, if I wish a higher gain of my circuit, I will actually have to sacrifice the bandwidth, because the product of the gain and the bandwidth is the constant equal to so-called unit gain bandwidth of the amplifier. So, and in a data sheet, just this unit gain bandwidth is provided. So, for instance, for the typical amplifiers, maybe about 2 or 3 megahertz. So, what does it mean? So, I may construct and I'll design an amplifier with a gain 1, and it works without any frequency, without amplitude frequency distortion up to 3 megahertz. If I design the amplifier with a gain 10, so I may work up to frequency of 3 megahertz divided by 10, 0.3 megahertz, 300 kilohertz without amplitude distortion. If I wish to have a 100 gain, so I will get the bandwidth only up to 30 kilohertz, up to 30 kilohertz without distortion. So all the way the circuit gain and the bandwidth product is the same 3 megahertz without any. And another frequency related parameter of the amplifier, which is as important as a single gain bandwidth, is so-called slew rate. Actually, this slew rate is limited by this recharging of the internal capacitors, and the slew rate is specified as a voltage increase, as a velocity, actually, velocity of the voltage increase in the amplifier. So, if we have so actually the maximal frequency we may operate with this amplifier is defined not just by this bandwidth, but in some extent more important is its slew rate. So for instance, so the slew rate, for example, here is expressed at 15 volts per microsecond. So it means that maximal derivation, actually maximal velocity of the signal increase on the output may be only 15 volts per microsecond. So if we select such a high gain that that the signal have to grow faster than 15 volts per microsecond, our amplifier will distort our output signal. So, and from this point, from the slew point rate point of view, so I may calculate what will be the maximal frequency I may work with by knowing the slew rate of the amplifier and defining what will be the maximal amplitude on the output I will work with. So it's seen that the lower amplitude I will take, the lower will be my gain, and the lower will be the output signal range, the higher frequency I may afford. If I'm going to use all the range of output voltage is what is available for me, for example, plus minus 5 volts or plus minus 10 volts, I have to take into account that at such high amplification, such high gain, and such high output range, I may just go to distortions on the frequencies that will be lower than those predicted by the unit gain bandwidth. Yeah? So this should be taken into account too. So the slew rate. And sometimes the amplifier have a perfect bandwidth of 3 mega, 1 megahertz, 3 megahertz, but it couldn't work with the high voltages, high frequency signals just because the slew rate is small. It may work only with very, very small amplitude output signals. Well, okay. So so this is some actually summary of what actually we may expect from the real amplifier from the frequency response point of view. So that actually distorts signals. The offset voltage, as I said, it's related with the difference in a base emitter bias voltages of the input stage of the amplifier. So they are actually not equal, absolutely equal, and they may not be absolutely equal to get the output voltage equal to 0. So there is a different procedure. Sometimes we just ignore it. So if an application is not very important, it's not necessary to work with very teeny signals, we may just ignore it, and very often is done. Or we use such kind of zeroing procedure for the very precise, for the high precision amplifier circuits. We may use an amplifier with a zeroing possibility. I have to show. Is it? Yeah. So here is an example of the connection of real op amp with a zeroing possibility. So we have this famous 741 amplifier. So we actually has a special output, the first and fifth in this case, when we attach a potentiometer connected with a slider to the negative power source pole. Yeah? And actually the zeroing of the amplifier happens in such a manner that we attach a same voltage on the input, both inputs, and then we adjust the potentiometer. So we actually adjust it to get the accurate 0 on the output. So with the zeroing, we may actually remove this bias voltage. Some of the amplifiers are manufactured without the zeroing, just taking the case, this offset voltage is low enough, and we just ignore it. This offset voltage sometimes change because of temperature, because these differences base emitter currents because of temperature may cause change in this offset voltage. To prevent this, if you really need a very high accuracy, so there is some kind of thermostabilization used to compensate for this offset voltage drift, or use an MDM approach when this offset, the DC offset are actually eliminated by using operating in alternating current mode. The noises are related with an offset voltage. This is a called flicker noise, which is reciprocal to frequency of the noise, and so-called popcorn noise. They are actually caused. These noises are caused by the some fluctuation of the base emitter currents. The bias currents, as I said, so the bias current, which actually flow through these input stages of the operational amplifier, for the transistor amplifiers, this may be as low as 20 picoamperes. If the input stages are field effect FET transistors, the current may be even lower. What is important to remember that the current actually flows through feedback loop. So this provides a additional voltage on one of the inputs. So I just draw example here. To draw here an example. So if we have a typical non-inverting amplifier is RE and R feedback. So what actually happens? So let me take this. Here we have some negative voltage U input that is lower than 0. So I have here some positive voltage. Then I have a bias current that flow this way. So this bias current actually add some additional voltage to this point, plus some delta U, which is equal to R feedback times bias current. So it means that this point will be at a little bit different, voltage than this point. The amp try to compensate this difference. That's why the output voltage will be shifted a little bit. So it will be U output plus some delta U, which is related to the voltage produced by the bias current flowing through the feedback resistor. To compensate this, we actually have to provide to compensate for this current, we add the resistor, just dummy resistor, in the to the other input. For this case will be inverting input. So with resistance which equal to the resistance of, with a parallel resistance of the input voltage and feedback voltage. So actually the current that flow through this, in other words, very briefly, in other words, so the current that flow here through these two resistors cause here an additional voltage drop. To get the same voltage drop on the opposite input, on the second input, we just add here the resistor, which is approximately equal by this parallel resistance. Yeah. So then the bias current through the second input will cause the same voltage drop, the same voltage increase here. And this voltage increase simultaneously, as they appear simultaneously. They doesn't give any extra addition to the output voltage. So this is one of the solutions to take this additional compensation. Another solution, just to reduce the feedback resistor to minimize the voltage drop. And then, but for this we have actually used quite low resistance on the input, and this gives us quite high input current for the whole circuit. The temperature drift doesn't affect bias current much, just because they are in the same direction. They appear, they synchronically, this change in the input currents, they appear synchronously on the both inputs. They doesn't provide any change in output if we has this compensating resistor. So, some other aspects about the noises. Yes, about the noises. So the source of the noises is quite plenty of source of the noises into the op amp itself, and this is a noise in input. This is a noise of internal current sources and so on. Actually, the noises very often is related to the resistors, which are included into the operational amplifier circuit. To minimize one of the recepts to minimize noise, usually we try to reduce one of the principles to reduce noises to take the feedback resistor lower than 100 kilo ohms. So this is one of the receipts. So when we discuss what resistor should we take for the input and output, so for the output, if we use a compensating resistor, so this idea of keeping the resistor, feedback resistor about 100 kilo ohms is probably not so important if we use this compensating resistor in the second, for the bias current in the second input. But what actually is in a concern that the feedback resistor shouldn't be very high, because very high resistor cause high temperature noise. And to reduce noise, the feedback resistor should be less than 100 kilo ohms, and even better really to keep it around up from 10 to 50 kilo ohms. This actually limit the feedback resistor, and due to this it limit actually the input resistor if we are going to get a certain amplification, certain gain of the circuit. So it's not like say it's like a law, but it's like kind of rule of thumb. So if you're going to minimize noises, the temperature noises in your circuit, you actually should limit your feedback resistor up to 100 kilo. So theoretically, it's possible to make a one-stage amplifier with, let's say, the input is when the input is with amplification, the input resistor is 1 kilo ohm and feedback is 1 mega ohm, so 1000 amplification in one stage. But it's a bad solution because of high noise level in this 1 mega ohm feedback resistor. And the second, with such an amplification in a single stage, the slew rate of your amplifier should be very high. Some comments up to input impedance. So if I will not discuss it now in very high detail, just to make note that if we consider the real amplifier, so for the bipolar junction amplifier, transistor amplifiers, the input resistance, the differential resistance is about 2 mega ohm. For the FET transistor amplifiers, the differential resistance is about 1 tera ohm, so it's much more higher. But this is a characteristic for the open loop circuit, so when there is no feedback. So if there is a feedback, so we may calculate when the amplifier works in a feedback loop, like a follower, we may demonstrate that the effective impedance on the input, which actually is calculated as a ratio between the increase in the input voltage and the increase in the input current, so we may demonstrate that this effective impedance will be actually the differential impedance of the amplifier itself times the amplification, sometimes the gain of the amplifier, so it will be very high. So the input impedance of the follower is even higher than the input impedance, differential impedance of the amp itself, because of this gain effect. So it's very high indeed. So let's consider one. Even for the bipolar junction amplifier, we have 2 mega ohms, which have to be multiplied by 10 in the power of 5. So we have a giga ohm effective amplifier, effective impedance. The same, yeah. Well, for inverting amplifier, of course, the input impedance is just an input resistor, just an input resistance. So for inverting amplifier is not the case, but for the follower and non-inverting amplifiers, so the input impedance is really very high. The output impedance is the same, so we have to consider all the circuit, including the feedback, and for an output impedance, which is actually for the typical amplifier, it's about real impedance is much more lower. So, and if we calculate here the change in the output voltage caused by the change of the output current and the corresponding change in output voltage, so we will find that the output impedance is much more less than the output impedance of the single loop amplifier. So the follower indeed makes this circuit quite effective. But nevertheless, when we speak about the useful load, so it's better to have the load of the amplifier. It's about more than 500 ohms. So for these loads, an amplifier works perfectly. Here, a special attention should be paid if we have a very high capacitive load on the input, because this output voltage, output impedance, and capacitive load will works like a filter, like a low pass filter, suppress and high voltages, high frequencies sometimes. Okay, this is actually a short view. Actually, with this, we end our review on the amplified circuits, and we actually stop for today. We meet next week, and we will discuss the analog measurement devices. I think that probably the next class we take. Oh no, I don't think. I just put some example on calculation of the AC circuit with the amplifiers as an example for your individual, for the individual study. Yeah, but have not done it yet, but I will try to do it this week for you to review it by your own, and we will take just a new topic next class. Okay, thank you. Any question, please? Is there any question up to now? Okay, if no, so thanks a lot for attention, and yeah, see you.